welcome to Classical Mechanics 2. In this video, we'll derive a very special functional that physicists use to describe the dynamics of many complex systems. It's called the Lagrangian. The Lagrangian is defined as the kinetic energy minus the potential energy. If I were to write this out, I get 1/2 mv squared minus the potential energy as a function of position. The Lagrangian is then a functional of position, velocity, and time, where position and velocity may themselves be functions of time. If we want to find the trajectory of a system, first we work out its Lagrangian, then we use the Euler-Lagrange equations to solve for the optimal path. Let's look at what the Euler-Lagrange equations are telling us physically for a particle that's only moving in the x direction. The Euler-Lagrange equations are dl by dx is equal to d by dt of dl by dx dot. The left half of the Euler-Lagrange equation, dl by dx, is equal to minus du by dx because the kinetic energy is not a function of position explicitly. And we know that this is the force in the x direction by definition. What about the right side? dl by dx dot is equal to mx dot, which we know is the momentum in the x direction. So what the Euler-Lagrange equation then is saying is that the force is equal to the rate of change of momentum. So this means that the Euler-Lagrange equations are the equations of motion for my system in each of these coordinates. If we think about this in terms of the calculus of variations, we get the so-called Hamilton's principle. First, we need to define a quantity called the action. And the action is the integral from time t1 to time t2 of the Lagrangian dt. This looks just like our I integrals in the calculus of variations video. Hamilton's principle states that the path a particle takes is the one for which the action is stationary or minimized. Since this setup is identical to how we derived the minimization of functionals, we know that the Euler-Lagrange equations are guaranteed to give us a stationary action. This means they give us the dynamics of the system. Given that the Euler-Lagrange equations are just another way of writing F equals ma, why do we use them rather than Newton's equations for so many IRL physical problems? The concept of generalized coordinates is the reason that the Lagrangian method is so much more powerful. Imagine we have a change in coordinates. This could be something that's tied to the geometry of the system, like a transformation from Euclidean to cylindrical coordinates, or something that's much more easily measured within the system, like the distance a block has slid down an inclined plane. We'll call our new coordinates qi's, and these are functions of our original Cartesian coordinates r, where the index I runs over 1, 2, 3, which correspond to the three components of r, x, y, z. In my original coordinates, the Lagrangian is given by 1/2 m r dot squared minus the potential energy as a function of position. This is going to be equal to the new Lagrangian in terms of the new coordinates q1, q2, q3, and their derivatives. Hamilton's principle states that the action for this system, whether it's expressed in terms of the original Cartesian coordinates or the new so-called generalized coordinates, is going to be the same. This action is the same action as it was in Cartesian coordinates. And that means that the dynamics satisfy the Euler-Lagrange equations in the new coordinate system. So these dynamics are given by dl by dqi is equal to d by dt of dl by dqi dot for all I. There's one caveat to this, and that is that the qi's have to be an inertial coordinate system for the physics to make sense for these dynamics. We can extend the definitions of force and momentum using the Euler-Lagrange equations for the generalized coordinates. So our generalized force is dl by dqi, which is our generalized force in the qi direction. And the generalized momentum, dl by dqi dot, is the generalized momentum in the qi direction. These quantities might not have a physical interpretation. So when I say in the direction, they're not necessarily vectors, and they can't necessarily be added by vectors. But we're going to find that these are very useful quantities in calculating dynamics, in particular when we study Hamiltonian systems. For a first example, let's work out Lagrange's equations for a free particle in 2 dimensions. Our particle is traveling at velocity v. Then its Lagrangian is given by 1/2 m x dot squared plus y dot squared minus the potential energy as a function of x and y. I get 2 Euler-Lagrange equations for the dynamics of this system, one for x and one for y. This tells me that the force in the x direction is equal to minus the derivative of the potential energy in the x direction. So those are Newton's equations again. And since these are symmetric, I get the equivalent equations for the y direction as well. What if I wanted to solve this in polar coordinates? This is one type of change of coordinates I can do. Then the velocity is going to be the time derivative of the position vector in polar coordinates, which is r cosine theta in the x direction plus r sine theta in the y direction. Then the kinetic energy is equal to 1/2 m times r dot squared plus r squared theta dot squared minus the potential energy as a function of r and theta. Before we work out the Euler-Lagrange equations, I'll write down the definition of force using the definition of gradient in polar coordinates. We have minus du by dr in the r hat direction minus 1/r du by d theta in the theta hat direction. The Euler-Lagrange equation for r is dl by dr equals d by dt of dl by dr dot. This gives us 2 terms on the right-hand side coming from derivatives of these 2 terms here. And that gives us mr theta dot squared minus du by dr is equal to mr double dot. This is telling us that mass times the centripetal acceleration r theta dot squared minus du by dr is equal to mr double dot, which is the total force in the x direction. So the centripetal force minus the force coming from the potential in the r direction is equal to the total force in the r direction. Likewise, the Euler-Lagrange equations for theta state that dl by d theta is equal to d by dt dl by d theta dot. And here we end up with minus du by d theta coming from the potential energy and d by dt of mr theta dot coming from this term right here. This term over here is equal to r times the force in the theta direction, and this is going to be the definition of a torque. On the right, we have d by dt of mr squared theta dot, and this right here is angular momentum. So just from the Euler-Lagrange equations, we've derived that torque is equal to the rate of change of angular momentum, and that is equal to the moment of inertia I times the angular acceleration alpha. The thing that's really great about generalized coordinates is that you can pick any coordinates you want, and these can be designed to make your problem easier to solve. Usually what you'll do is you'll write down the x and y coordinates in terms of your new coordinates, q and q dot. You use that to define the velocity, and from the velocity you can use that to solve for the kinetic energy in terms of your new coordinates. And then you can solve for the potential energy in terms of your new coordinates as well. Then we'll just use the Euler-Lagrange equations, just as we did before, to solve for the dynamics of the system. Let's take a look at a couple of special cases or forms of the Lagrangian that makes integrating the Euler-Lagrange equations easier. We'll start with a form of the Lagrangian that does not explicitly depend on the position variable qi. That means that this term here is equal to 0. So we end up with d by dt of dl by dqi dot is equal to 0, or equivalently that dl by dqi dot is equal to a constant. Another case happens when the Lagrangian does not depend explicitly on time. This is a pretty common case. In order to see how this helps us solve equations of motion, let's write down the total derivative of the Lagrangian as a function of time. This is equal to the partial derivative of the Lagrangian with respect to time plus the derivative of qi with respect to time times the partial derivative of the Lagrangian with respect to qi plus the derivative of qi dot with respect to time times the partial derivative of the Lagrangian with respect to qi dot. So the partial derivative of the Lagrangian with respect to time vanishes because L does not depend explicitly on time. From the definition of the Euler-Lagrange equation, we can replace the partial derivative of L with respect to qi with d by dt of dl by dqi dot. Then what I'm going to do is undo the chain rule here, and I end up with d by dt of qi dot times dl by dqi dot. And this is equal to the total derivative of the Lagrangian with respect to time. So I can collect all of the terms and I get d by dt of the Lagrangian minus qi dot times the partial derivative of the Lagrangian with respect to qi dot is equal to 0. Or equivalently, I can integrate this and I end up with L minus qi dot times dl by dqi dot is a constant. Both of these methods convert the second order Euler-Lagrange equation into a first order equation with an integration constant that comes from the boundary conditions. We've spent a lot of time solving equations of this form using a variety of different methods. In the next video, we'll learn how to add constraints to Lagrangian systems and learn about the internal forces that they represent. Thanks for watching, and I'll see you next time.